记了。需要画图啊？嗨，Hello。
剪头发了，我卷毛的啊，
卷吗？
你看他还有嘞，他变得比较厉害。
谢谢。对，没有变那么厉害。
快来了，我想要读一下，我突然发现好像有个点用。
读得懂了，对吧？
我现在读懂了，发现觉得他写的很好。
这个是会变。
请挤出话筒。
但是我不太理解它的顺序。
比较奇怪的。
它的写作顺序我听不懂。
Okay, so 上个礼拜last week we got a suggestion. Suggestion that is you can bring typeset to the midterm. So this is a motivation for you to finish your typeset. So I will print for you. You don't need to print. I will print one copy for each of you. Since our class is small, and then typeset is quite standard, so we can do this. And then so how we'll determine what version to put in. So I think for now we have week 1 by Eric, right? Week 2 Larry, and then week 3 Jingsen. Week 4 switch to Lydia first, right? And then week 5 is Ivan, yeah. I think Ivan is working on it, so maybe we can push in a bit. And then week 6 is Yihang. And then week 7, I think up to this lecture, again, homology is not in the midterm, but I will try to go into homology this week. So by this week, this week is you as well. Okay. So by this week, I want Eric to help compile everything from week 1 to week until this week before homology. And next week is midterm, right?
Yes.
So next week, Monday, Eric will give me the final copy. I will print that version. Okay. So maybe another motivation for you is maybe I'll pick one question from the tutorial and then one question from our lecture exercises. Okay, so you can try and do as much as you can. Okay or not? Okay, does it make sense? Cannot, right? Yeah. Okay, yeah. I'm not sure whether I want to print the solution part or not, but you try first, huh? Because I haven't come up with the solution, I mean the question paper yet. Sorry?
I mean, when I do.
Definitely you combine everything. Definitely combine everything. Then I will see whether I want to print the solution. Just as a lecture where first. Yeah. Just as a lecture the lecture sequence. In lecture sequence. But maybe you can help with the proofread. And also for those who take care of each week, right? Maybe sometime I will update the notes after the week. So please check it out. Update your note as well. 不会，那个我就不理他了，反正一直改也是会变的，我没有改起来。啊？AG 怎样？AG 怎样？
你整稿的就大家一些
Yeah, I could do that after this lecture. I could do that after this lecture. Yeah. Pre-read, I won't touch anymore. But once I finish the core emoji part, I will upload for the core emoji one. I think we don't have time, given that chapter 1 already take out 6 weeks. I think homology also around the same. Yeah. Fastest is 5 weeks also. So homology, I think we have to cover, of course, the definition, and then most importantly, the cup product. I think this is something that we don't see in homology, and then perhaps point correct duality. I think those are quite pretty big stuff. Homotopy theory, is not sufficient to just go into homotopy theory, because if you really read the homotopy theory part, right, a lot of things you cannot compute there. You cannot just compute by definition. And then you need to realize on something called vector bundle, which is K theory. Okay, so I think to learn homotopy is better just go and learn the K theory. Yeah. Oh, that's very ambitious. Unless we got like 50 people want to learn algebra, maybe we can have those courses. Moduli spaces. Yeah, that one is even more hard. Yeah. Modular spaces appear everywhere. Yeah, as long as you have a parameter space, you are modular space. Okay, so I think we have finished up the covering space part. Next section, we will go pretty quick because it's just and let's see the space that we learned before in a different way. Okay, in particular, in this last section here, we want to see every topological space as a covering space. Okay, we want to see every topological space as a covering space. So a covering space of what? Okay, we will try and construct it. So before that, we will talk about covering space action here, or covering space condition. Okay, that's the certain action of the deck transformation that's satisfied. Okay, so what's this covering space condition here? So if you are given a deck transformation, okay, this is what you will automatically get. Okay, so how you interact with the definition of covering space. So covering space, we really only care about the open neighborhood, right? There's some disjoint open neighborhood. So meaning if for every point in your covering space, okay, there is some open neighborhood, okay, containing a point such that the intersection between the action of two that transformation on the open set is non-empty, then this two has to be the same group element. Okay. So if you have two elements that add on every point such that there's some open set they are intersecting non-empty, they are actually the same element. Okay, so this is a very interesting property of deck transformation here. In other words, if you just look at U and GU, it's non-empty. For every point that exists some open set like this, then this G actually is identity. Okay, actually you are not moving far away. Okay, you are not moving far away actually. Then this is called a covering space condition. Okay, so this proof is quite I think actually it's just group theory plus a general topology. So I think you will understand it. You read it. Then what we're gonna do is, let's say we have this kind of action, then we can form the quotient space. Okay, so this quotient space is exactly the G orbit space. Okay, we put all the orbit into one element here. Okay, so this orbit space. Okay, so orbit space is very ubiquitous, right? Agent. Okay. Very common, right?
Action.
Yeah, for example, the quiver variety unit. Okay, so you can think of it as a quotient space or the orbit space here. And then what's the property of this space here? Actually, this will make your Y into a normal covering space. Should still remember what's normal covering space mean? Normal. What's normal covering space mean? Some Yes. Yes. So the pi one of this covering space will be a normal subgroup of the which group? Which group? Fundamental group of the original space. Let's check. Fundamental group of the space you are covering. So meaning the pi one of your orbit space. So the image, okay, the pi one image under that P, okay, is a normal subgroup of your pi one of your orbit space. Okay, so you can apply this proposition. So the proposition we discussed just now is coming from the proposition we had last time. And then G is the group of transformation because this covering is normal. Okay, and then lastly is this G can be realized as a quotient of the pi one of your orbit space. Okay, apply the previous proposition. So the main point here is to prove that it's normal. Okay, and then the rest you can apply what we had before. So to prove it is normal, again, is a general topology argument. So we skip. Okay, you should be able to understand. If you don't understand, you can ask and then we can try to discuss. So this covering space action, right, is very special. Okay, let's compare with these other two kind of action here. So one is properly discontinuous action, and then the other one is free action. So any group action that has this covering space condition, right, is called a covering space action. And then what's called a properly discontinuous action here? Okay, so this action is an action such that each point also has an open neighborhood such that this non-empty intersection here only apply for finitely many G. Okay, finitely many G. Just now was every G, right? This is only for finitely. No. Just now was this condition here will imply the G is identity. But this condition, this allows G which is not identity. Okay, properly discontinuous. Okay, so properly is a proper, I think, finitely many here. And then it is disconnected at some point, some action. Okay, so let's look at the discussion between the covering space condition action and proper here. So let's look at this group of symmetry here. Tiling of R2 by regular hexagon. Okay, so does anyone know what is tiling? I think Jingsen know very well, right? What is tiling? What is tiling by regular hexagon of R2? Countable? What do you mean countable? You just need countably many regular hexagon. Okay. So what do you mean? What does it mean by tiling of R2? Okay. Cool. Okay. So here is R2, right? Your plane. Okay. So you can think of this floor, but this floor is tiled by regular square. This tile is regular square. So we're gonna change this square into hexagon. Yeah, exactly. Exactly. Yeah, exactly. Okay. So we say that this has a proper discontinuity property, but not covering space property. So let's check. So why it fails the covering space condition here? Because there are fixed point. Okay, so there are fixed point like the vertex of the hexagon. Okay, so this is fixed by a 2 pi over 3 rotation about this point. Okay, so 2 pi over 3 is what kind of angle is that? Like so I mean no need to know the angle, right? The point here is maybe let's draw it. The point here is you divide the circle into 3. So I think it's 100. Okay, so what 220 100 rotation is like you rotate the whole plane. Okay. So can you see that this is like 120 from each other? So you rotate everything by 120, you get better same picture. You get the same picture, but every point rotated except this point. Okay, so then this point definitely you can't find any neighborhood such that the G that fix the U, I mean, getting the non-empty intersection to be just identity, right? Because I already provide a non-identity element such that you add on this point here, the open set will still intersect with the original open set. Get before and after the action. Okay, no? Okay. Similarly, it says that if you pick the midpoint of these edges, you just take a pi rotation, you come back to the same. Okay, so these are the fixed points. But this property is okay for the properly discontinuous action here, because it will be only true for finitely many G. If you do other symmetry, then you won't have these fixed points. Okay, for example, the midpoint of edges is not a symmetry for 2 pi/3 rotation. Okay, next, more general action is called free action here. Okay, so what is free action? Any action that without fixed point is called free action. Okay, why is it free? Because there's no fixed point. So the covering space condition actually imply a freeness. Okay, maybe you can try and do this exercise. I forget it's whether hard or easy already. Maybe it's not hard. Or either it is very tedious on not using, using general topology stuff. So the converse is not true. For example, if you look at the action of Z on X1, in which a generator of Z is fed by rotation, through an angle alpha, there's an irrational multiple of 2 pi. Okay, so this is a bit weird. It's an irrational multiple of 2 pi here. So once we have this irrational, right, so from analysis, you know that irrational is dense. Okay, so we're going to use this to contradict the covering space condition here. So each orbit ZY is dense in X1, so the covering space condition cannot hold. Yes, since it implies the orbit are discrete subspace. Okay, if covering space condition hold, meaning the intersection must be empty, so they are discrete, but they cannot be. Okay, they cannot be discrete. So it must intersect the open set after the action. Okay, so in general, right, for action on a Hausdorff space, once you have freeness, you get proper discontinuity, and then you get covering. And this is for Hausdorff space. Okay, let's look at some example here. Okay, so 海星叫什么来着 ？Starfish。海星叫什么来着 ？Starfish. Okay, yeah. So you can see that this starfish-like topological space here. Okay, so this is a covering space for C. Okay, so how do we see this as a covering space of C then? So you can see that there's some symmetry here. Okay, so in particular, a 2 pi/5 rotation is a symmetry. Yeah. Because if you turn 2 pi/5 is still the same starfish. Okay, then if you quotient out by this orbit here, meaning you have 5 orbits, right? You quotient out the 5 orbits, then you're left with 1 orbit. So you're left with one of the arms of this starfish. Does that make sense? Does it make sense? Okay, you can generalize this idea. You can increase the whole or increase the symmetry, rotation symmetry here. So in general, you can prove that you have a mn plus m m m of mn plus 1 to mn plus 1. So the small m here is the genus. Okay, the n here is, I think, is the symmetry bar. You see, yeah, the n-fold symmetry. So you want to turn how many rotation? How many degree rotation? Okay, in general, you only have this. Actually, you can prove this, I guess. It's one of the exercise in the attention. Okay, interesting. Okay, let's continue. Maybe we skip this part here. Do we want to skip? Let's see. 肯定我今天就是目标要希望我去。Why？哪里？在哪里？你讲第二个哈？哦，yeah. OK，终明白。How about let's go through this one because this will see how we define the simply connected covering space for X1. Okay, so for covering space action for a group on a simply connected locally path connected space here, pi 1 of y over g is isomorphic to g. Okay, so this is a very good statement actually. So as long as you have a group action on a simply connected space here, so if you take your simply connected space, so in particular, the universal cover is a very good choice here. Okay. And then if you quotient out by the G orbit, then the pi 1 is actually G. The pi 1 is actually G. Okay, so how to prove this? Are we proving this? Actually, we are not. Maybe one can try and prove this. I think not too hard. Yes. Yeah. So then this is exactly how we compute this is one of the other way we can compute pi 1 of x1 because we can realize x1 as the quotient of r by the z orbit. Correct? The quotient r by the z orbit we get s1. Okay, because we already identify every loop, every loop, not every loop, I cannot say every loop, every, what do you call that? So you have your x1, right? You have your r1, you have your r, right? Okay, you have your r, and then by z action, meaning, say we identify these 2 points here, and then we extend this identification. So everyone will be identified to this group. Make sense? So for the blue part, they are the same point. Maybe for the green part, they are also the same point like that. So they are all identified into one loop. Similarly, you go downwards. So this is another way to get pi 1 of x1 is z. Okay, once we have this. Okay, next very interesting one. Let's look at R2. So we go up by level. Just now we got R. Now we got R2 now. So R2 we have some very obvious symmetry. One of them is translate. Okay, translation. So translation here. So there are 2 types of translation here. Let me see. Yeah. So for the first one is you just move up and move to the right. But how about the other one? How to describe? Let me see. It's of the form of x plus m y plus 2 n and then here Okay, so these two are different decorated grid in R2. Okay, so we want to find the symmetry on this grid. Okay, we want to find symmetry on this grid. So it is quite different. So for the first one, right, you can see that all the grid are the same. So you just do translation integer by integer. Okay, let's say the decorated grid here is an integer grid. Okay, so we just move by integer. But the next one, if you just move out by one, right, the arrow is different. Okay, if you just move out by an integer, right, the arrow is different. You can see or not? So you need to move two up, multiple of two, so that you can get the same grid, same direction. Does it make sense? You move once out, it's a different direction. Okay, it's not symmetry. So you need to move double in y direction. Okay, and then there's a second direction, second symmetry here called the glide reflection, glide, right? Glide reflection here. So this consists of a vertical translation by an odd integer distance followed by a refraction across a vertical line. Okay, either a vertical line or a vertical line halfway between two edges. So do you know what it means? So meaning, although right, you move out one grid, it's not a symmetry, but you can just reflect everything along vertical line. Does it make sense? Because the direction is wrong, right? But once you reflect, the direction will become correct along a vertical line. So this is called a glide reflection. So you have to glide first, only you do reflection. Make sense? Does it make sense? Okay, so you move up by one, the direction is wrong, never mind, do a reflection. Then you will become the right direction. Okay. Okay, so maybe interesting, you want to guess or not? If you take the orbit of this action, right, what is the topological space you get? So for example, the first one, right, you identify these two. If I identify these, what's this? Can you imagine? Top, bottom, same direction. Fold. Someone? No? You fold top and bottom, right? And then you fold left and right with the torus. Okay, so the first one is a torus. How about the second one? Yes. Prime bottom. Okay, so R2 mod by G is torus and R2 mod by H is prime bottom. And then because R2 is simply connected, so the pi 1 of R2 mod G is just G. And then pi 2, wait, why pi 2? Pi 1. Okay, pi 1 of R2 mod by H is also H because H is simply connected. Okay. All right. Next one is we also can view RPN as this kind of construction here. So how do we do that? Basically look at Sn first. Okay. So Sn has Z2 action. So meaning you send X to minus N. Then RPN is just the orbic space of Sn mod by Z2. Okay, maybe right here. Okay, so you can prove that this is a covering space action. So since Xn is simply connected for n greater equals to 2, pi 1 of RPN is isomorphic to Z2. Note that here we put n is greater or equals to 2 because what is S1? S1 is not simply connected. Okay, so if you want to compute pi 1 of RP1, there's a bit different. Pi 1 of RP1 is Z2 cross something else. Cross Z if I'm not wrong. Okay, so we only know that pi 1 of RP 2 and above is Z2. Okay, and then you can find that actually the generator of this is any loop that obtained by projecting a path in Xn connecting two anti-border paths. Okay, so there's a question inside your capture, right? There are actually only limited finite group that can add on Sn. Okay, because the one we have now was Z2, but actually they are limited of them, and then I think they already found all of them. Okay, so if you are interested, you can have a read of it and then write a report for that. Hatcher, nice thing about Hatcher is they provide a list of paper for you already, reference. Yeah, so you can study this. Huh? Oh, yeah, okay. 但是他也有嘛，对，怎么说呢？ Yeah， 对啊，我只说的啊。Okay, yeah. If you are interested, you can have a read more. So if you model by other finite group, what kind of orbit space you get? Okay. Next part is Kelly complexes. Okay, Kelly complexes. This is some kind of related to maybe something called Kelly graph or what. Okay, so Kelly complexes. So what's this Kelly complexes here? So again, you start with a presentation, okay, group presentation, and then we define what is called a Kelly graph first. Okay, so what is Kelly graph here? So for every G, okay, we put a vertex. Every good element you put a vertex, and then you add an edge. So how do you add an edge? You add an edge for every generator such that you can connect to G. Okay, so meaning what? So first of all, well, you definitely have identity, right? So your generator must be able to reach from identity to all your generator, right? Okay, and then for the rest, there's not a generator, then maybe you need to connect from some generators. Okay, connect from some, let's call it G beta. It's not in the generator. Okay. What do you mean by orbit? Yeah. Mm-hmm. Well, I mean, every H here will means that G alpha, so identity times G alpha, right? Okay, and then the other one maybe G alpha 2 times G alpha 1, like that. Okay, obviously identity also can go to G beta, right? You just use G alpha, you just identity times G alpha. Oh, cannot, huh? Can or not? Oh, cannot, right? Because yeah, just to all generator, because I think this generator, this generator, I think this generator is the fixed generator. Okay, so you cannot just randomly add generators here unless you add it in already, right? Okay. 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 Then we haven't finished yet. So this is just vertex and edges. Next is there's a relation here. Okay, so relation here will determine a loop. So once you get a relation, you will close this edge back to any starting vertex G. And then we attach a 2 cell to it. Okay, so meaning we make it a trivial loop. Does it make sense? You want to try an example? Maybe let's say G alpha 1, G alpha 2 is identity. So how do we close the loop here? Maybe the other way around. G alpha 2 times G alpha 1 is identity. So how do we close this loop? Okay, we start from identity, right? So identity, go to G alpha, go to G. So identity with this, then identity. So maybe we have to close here. Okay, so we attach a two set. Should I use a different color? Better see. Well, let's say, yeah, let's say G alpha I 2, G alpha 1 is identity, then we'll close this one here. Okay, and then the resulting thing is called a Cayley complex. Okay, so far okay. So one thing is the Cayley graph of G with respect to generator is connected. So this is just group theory because you can reach to every group element by multiplication only. And then for every multiplication, I add a path. Fair enough. Okay. And then second is very nice thing again for this cell complex here is pi 1 of this, we call this xg. This xg is actually just G. Oh, come back to G. So what to do here? Wait, let me see. Oh, so given this group presentation here, we can construct its two cell complex such that two cell. Wait, let me check first. Okay, good. So yeah, I think is this what we have learned before? Huh? Is this what we have learned before? So given a group presentation, we can construct yeah, this is what we learned before, right? So we have a group presentation, we construct a topological space such that pi 1 of this topological space is just G. You still remember? This is how we say that we can realize every group as a fundamental group. Okay, using this two-dimensional cell complex here. So what we do was we take a wedge sum of circle and then one for each generator, and then we attach a two cell. So what's the connection between this construction and the Cayley complex? Okay, actually the Cayley complex, right, is a normal universal covering for this complex we had before. Yeah, very interesting. Okay, so very simple construction become the universal covering. Okay, moreover is normal. Okay, moreover is normal. Normal means what? Meaning that the image of the pi 1 is a normal subgroup of G. Not definition. Oh, the definition is for every 2 points in the covering space, you will have a depth transformation between every leaf, right? Okay. Again, this proof is quite straightforward. But let's see how we view our space as this kind of construction. So let's say we take the easiest free group you learn is group by generated by two elements, right? There's no relation here. So then what is this xf2 and s tilde f2 here? So if you take which sum of two circle A and B, and then there's no relation here. So this is really just two wedge sum. So x1 wedge s1. But then but then what is the Cayley complex here? Okay, so but then what's the Cayley complex here? So what's the Cayley complex here? So Cayley complex says what? If you have an identity, then you will connect to all the generators. You have A and B. Okay? And then obviously you have A squared, you have B, right? And then B maybe go to BA, and then go to B squared, something like that, and so on. Okay, so if you grow this thing out, this is the universal cover that we have done last time. B here is B, here is A, here is A inverse. Okay, makes sense. This actually also matches up with our universal covering construction, whereby you view all these points as a homotopy class of path. Okay, so every point here is a homotopy class. Okay, good. And second, next easiest one is a abelianized version of this F2 here. In that case, what you will get is, again, on SG is just X1. Oh, so SG become X1 cross X1 is a torus already. Okay, because you have a two-cell. This is the two-cell relation for torus, right? A, B, A inverse, B inverse. So the wedge sum you glue together become a torus. And then the universal cover is a R2. So I think I draw a picture on how you glue the picture from covering space, the universal cover for X1 versions. So this is how we do it.
这个难的
Two cell. Yeah. So this relation coming from your commutative relation. So this green part, this blue part is two. Okay, how about Z2? Okay, what's Z2 then? So if you have a X1, okay, you glue by A square, you get RP2. Then how about the Cayley complex, what? Okay, how about the Cayley complex? How to think about Cayley complex here? So you have identity, right? And then you have A, and then obviously you have A square, and then you have a bunch of A, probably. But we know that A square will come back in so many informal loops. Okay, and then you attach two cell. Right. Is this S2?嗯，什么意思？里面转回来啊？
是是
有个圈圈，他们艺术啊sure. And everything. You mean you got infinitely many loops? Huh? Wait, let me check first. Let's check the definition again. So we attach the such loop. Every relation determine a loop. Oh, should we do that? No, I think under those relation, those elements already disappear, right? Those elements are just A and A square. Yeah. But the point here is we join this A square to identity here. Then we glue a two cell. right? We glue a 2 cell, but is this S2? How is it a X2? Supposedly we should glue another one at bottom. Why is this an S2? Maybe. Wait, if we get the A square equals to identity, I think we also have A inverse, but A inverse, what is this? A inverse and A inverse is identity. I think this will provide another 2 cell, right? So one you glue A2, then you glue A minus 2. Does it make sense? So you have here identity, right? Equals to A2, and then here you got A here. Right. So one, if you glue from the top, and then again you glue from the bottom. Does it make sense? So one, you glue A square, and then you can glue a bottom. Okay. If A square equal identity, A minus 2 also identity, right? Yeah. Because A is invertible. Because it's a group. Okay. Yeah, so I think bottom here got the draw here, got draw here. So anyway. Yes. What do you mean? 什么？这两条线什么意思？哦，这两个 group one 是 X2， you got 2 cell. Okay, but in general, I think it's this. So in general, it's this. So this X tilde of Zn consists of n disk with their boundary circle identified. Just now we got 2. Just now we got 2, right? So 1, 2 cell at the above, 1, 2 cell at the bottom. Then in general, is n disk with their boundary circle identified. Okay. Okay, ma. So one you glue along A square, the other one you glue along A inverse A to the power negative 2. Okay, because secretly there's another relation, right? So this supposedly is A plus and then A2 A minus. Okay. But I think they are the same actually. Okay. Okay, so far, okay or not? Okay, let's continue one more. Yeah, maybe one more, we can take a break. So one more, if you take a free product of Z2 cross Z2, what do we see? Okay, last time we see that this is a symmetry of what do you call that? Integer point on R, because you can translate infinitely many times, and then you can reflect at 0. Okay, so which is a semi-direct product of Z with Z2. Then what we see here is, if you just consider the two-dimensional cell complex correspond to this group here, this is actually an infinite sequence of tangent two spheres. So tangent two sphere means what? They meet tangentially. Right? They meet tangentially. So this is I think this should remind those who take algebraic geometry before it. This is like the exceptional divisor for the type A singularity. But this one is infinite. Okay, this is infinite. Yeah. So and then let's say if we look at the one of the normal subgroup of this group here. Then what? Wait, let me see. Did I write something wrong here? Okay, let's see what is going on here. So the elements of the index 2 normal subgroup Z in Z2 star Z2 here generated by AB. Add on this X tilde here. Wait, let me see. This is X tilde or this is X? So let's see, this is X or just X tilde. Is this a Cayley complex or two-dimensional? Let's think about it. I think this is S tilde. This is S tilde. This is not the Cayley graph. This is X tilde. Sorry, this is Cayley complex. This is not the two-dimensional Snell complex. Because two-dimensional Snell complex, what you do was you take the generator as a wedge sum of circle. But here, if you look at this circle here, actually it's not just B itself, right? But instead, you take from identity element. Okay, you make an X to a group element B. Okay, so this is actually S tilde, not X. This is X tilde. So then, next is we look at the group action on this thing. So what's the group action here? This is something generated by AB. So you see what happened now if you do AB here. So if you do AB, you move like this. No? So what does it mean if you move AB? So you move like two circle, two sphere away. Okay. So actually it's a translation by an even number of units here. Okay. So it's like 2 by 2. You move 2 by 2. But obviously it's a symmetry, right? Because you just translate by 2 sphere. Okay, it's still the same infinite string of sphere. But then there's a very special things happen. While each of the remaining elements of Z2 cross Z2 act as an antipodal point, antimodal map on one of the sphere and flip the whole chain of sphere end to end about this sphere. Wow, does this make sense? Does this make sense? So it says that other than AB, all the rest of the elements will act as an antipodal map on one of the sphere. and flip the whole chain of sphere end to end about this sphere. Okay, let's think about how to understand this question, this statement here. So maybe let's look at this one. Yeah, I mean, yeah, let's look at it. I mean, how about look at this sphere here, and then we move by B. Okay, we move by B here. So if we move by B, then what happens here? If I move by B, then everything will go to the left once. Right? And then what's the next thing you do? Yeah, let me check. So if you move by A to B, then if you move by B, move by B, okay, so if you move by B, what happened was there's only this sphere, the sphere that contains this B get affected, right? So can you see that if you move by B, what happened is this point here will go to this point. And then swap these 2 points basically. Okay, swap this 2 point here. So how to read about this how to read about this this action here? Then it says that it is an antipolar map on one of the sphere. Correct or not? So left to right, right, antipolar map. And then flip the whole chain of sphere end to end about the sphere. So meaning away from this sphere, right? It stop. Does it make sense? Yeah, just yeah. The two infinite string like swap place. So this end here will go to this end, and then similarly the other end here will move the other end. This will just imply that all the rest also get swapped. I don't know. Does it make sense? Does it make sense? So imagine about this sphere here. So this point here come to this point, and then the left point go to the right point. Okay. Also, obviously, this is true for the rest of the sphere that contain B. But the way to talk about it is I can swap this with antipolar point or antipolar map, and then I just swap M to N around the sphere. Correct? Because this also will swap all the other sphere with B. Okay. And then this orbit space here will be RP2, which RP2? Because you already identified 2 by 2, and then you have this opposite antipolar map. Okay, and then similarly you can do for the rest, like Z2 free product with Z3, then you will see something like this fractal thing coming up again. And then similarly, you can do it for Zm star with Zn. If you want to do a project about this, also can. Maybe you can try and draw it up. Okay. Yeah, I think that's it for covering this stuff. Any question or not? Any question?
下一个手工，
啊？什么？
下一个手工。
Yeah. Okay. Any question for chapter 1? Finally, we finish. Chapter 1. Yeah. Final 什么？
我
啊，还能要怎么好很多？应该就是 homology 吧。homology 我们不会伤到太多。
就你早就2000，
嗯，对，不够哈。啊，杀掉了，我觉得很多了啊，因为because 我跟你讲发生什么事情吧，因为我们有花了一点时间在 self complex 上面，比如说我们老师教这门课的时候，他们没有花时间在 self complex 上面，他只是 assume 我们会这样不然呢，他就 assume 我们会这样，好像我们会画 climb bottom，我们很会画 chorus，我们很会 RPM。哦，that's why 为什么我会 stress on 这种 RPM 东西？为什么我们有开了一个 Algebraic geometry 的课，就是这个原因，就是让你们看更多的这些 RPM 的。那时候我们就是一下来就是好像你感觉你很会了，这 space 好像你天天吃饭这样，很随便就掉出来。Yeah，什么？Yeah，so that's why 我们会花比较长一点时间在 Chapter One，because 等一下我们还会用到这些 self complex 的东西。Yeah，没问题。艾文在哪里？我不知道。有没有在？
这不会
嗯
自由了，花年就年。
，Yeah，年哦，用年做出来。Okay，let's break until 10:15 呢。if you want to chit chat, still can chat.
check 完，
Chit chat，
找到一篇里面，
什么东西？
这个礼拜要不要？
有没有去哈？哦，你要考试啊？考什么？
好难哦，靠北。
几时哦？可以发给我，
对了，
发给我看。
有点
看，你发给我看。去哪里读哦？你们？
哎，我没有选到，
学校啊，
我本来选的，
哦，你们 G1啊？这样的话，你下个礼拜也没有来咯，我们也没有 meet 哦。
下个礼拜没有米，没看去，
上个礼拜又没有，下个礼拜是那个 differential manifold。
哦，下礼拜你们有没有空的？
我可以换天的。
下个礼拜
你要换天？你要换哪一天？
有空就可以啦。
可以哦，可以啊。再说，如果个别需要，你发给我，你发给我。要，yes。
我听别人讲很难的，我就没有。
黄瓜的韩语叫欧美，
我那个我有一个那个我在做 Type C 码的时候，我发现到在讲这个一个这个同义是多比图这个 S 方跟 X，这个是我用顶写啊，他讲给我一个写条论，完全没有听过，被多的，对，有什么办法可以我看到这？对，不是的，
I think 我们用图罢了吧，这是 homotopy equivalent。
是我们都比可能
想一下哦。哦，OK，首先你应该要知道的是，为什么 R3可以在哪里？你要知道是为什么 R3可以，R3为什么可以homotopy equivalent to S2先？那你可就是全部东西收进来，外面收进来。
，Yeah，
I mean 把外面的东西先收进来先。
Yeah
OK，
information，
deformation ratio，对，deformation ratio，对，没有错。外面呢可以 deformation ratio 进来，但是里面呢要怎么处理呢？里面刚好有一个算是洞吧，或者是一整排的洞，不止一个洞。你想想看啊，假设这个不是洞啊，想一个比较简单的，假设这个是个洞，then 外面可以 deformation retreat 去这个boundary，然后里面也可以。但是有了这个洞哦，你不能 deformation retreat，因为你这个点不知道去哪里。 它会被拉扯开。但是如果这里是个洞的话，就可以。但是这个不是洞，但是它是一整排的东西被你拿掉，很多个洞
很多个洞，
拿掉。对，
那
对啊，你拿掉啊，你不是拿掉啊，你去掉它，你去掉一排啊，就是一圈的洞，
一圈的点是吗？
对，一圈的点，
一圈的点，
对，一圈的点。
可以。然
OK，
后这个，
嗯，这个是一粒洞吧，一粒点吧。
对，
OK，你去了一圈的点哈，说一圈的点，这些，你看这些周围要去哪里呢？对，这些周围要去哪里？然后我们的 claim 是这里面的东西全部去到这圈就好了，能够想象吗？
里面的东西，
对，里面的东西，当然不包括这个 S1，这个 S1被你丢掉。
去到这个圈。
对，
你的意思是它它的意思是可以用一些 mapping 转成这样子，是这个意思？
deformation restrict，
这是 deformation return。
对，
这个一圈
不是你不是 deformation restrict 这一圈，你 deformation restrict 里面的点，
里面的点，
对对，里面的点，里面的点。等一下啊，我来用其他颜色，这个是去掉的，这个你不可以。讲想象诶，
先收成一个结嘛，然
啊
后再把它拉长。
哪个？
这个里面的，
啊，
先把它收进一个点，
可能可以收去这个点哦，这个点，
收去一个点，然后
这个点哦，
再把它拉长，
这个点。然后
再拉长。我也不是很
没有，不用拉长，这些应该是也是从，我想一下，给我想一下，instead of 这个圈哦，你可不可以把它想成是，嗯，你可以把它想成是这样一圈，
对哦，这个圈还是这个圈？
这个青色圈，你可以想成这样子，
哦，这
你把它
就是有点像这样。
那个，
如果你的意思是它长这样，全部都是圈，我们里面是 fill out，就是这一整圈，
嗯哼，
好像是一系列的那个，就好像是包德一样，包，就好像医院这边空气，
嗯哼，
这个是 exclude 掉这些外面的圈啊。
嗯哼，
你的意思是这样子吗？
我的意思是它本来就一圈嘛，但是我可以 form 一个 cylinder，
应该是
因为他们是一样 homotopy 的，对吧？这个我是说这一圈跟这个东西是一样吗？这两个
这两个是地方美学，
我是拉
对，
长吧，对吧？对不
地
对？
方美学，
地方有一圈，所以我也是可以拉长哦。但是呢，我要解决这个点呢，
但是你这个为什么
啊，
是有上面跟
因为
下面？
哪一个上面是这样？
这个是跟这个，这是
我哪里有上面跟下面？
这个是地方美学，这个
对，没
对不对？
有错。
这个
这个我
这个有
绕吗？我绕它嘛，我绕你这个 S1，
哦，绕是 F1，
我绕着你的 S1啊。但问题是我要讲跟你解释这个点呢，这个点从哪里来？
是我 S1 为 S2，
对，他说怎么解释 R3 切掉 X1 过后是 X1 versus X2？所以你看啊，这一个你能够想象这一圈是哪里来吗？这一圈就是这个圈里面的点，deformation ratio 是一个点哦，所以就
嗯，
是有这样一整条线出来哦。 OK，然后这个圈以外的就 deformation retreat 回去这个 S2 上面了。OK，现在问题是怎么解决掉这个 wedge point？
我我
怎样
每一个
解决这个
每
wedge？
一个这样子的圈我都可以
嗯
这样子的点在里面了。
啊，对，
这样子这个
怎样解决 wedge point 呢？
which point 不跟 which point 不是把这个越来越小，就是
对，是的，
这个圈不是越来越小，哎也没有，好像就在外面了，
啊，
换一个圈，
哪里？
就是也是有个圈在这每个点，
然后到这边附近是发生什么情况呢？
对，不清楚，就是这样。
我想一下怎么解决这个问题？怎么解决呢？外面 OK 嘛？外面反正只是进来这边罢了。那里面 OK，你要看下这一圈发生什么事情啊？这一圈的意思是说，在这个里面会有一些点会挤过来，这个点，and then 这边有无限的问题在，就是有 infinitesimal 的关系在这边。然后我感觉这个角落跟这个角落要有一点解释
就解释可能是有 apply 到我们没有用过的，我看
啊，
到有一个 sequence 这样子，
对对对对，有一个 sequence，对对对对对，
我那个是
有一个
完全没有看过，
我们没有讨论到这样细，
嗯
呀，我们没有
大概大
讨论到这，但
概去
是但是我们要先 convince 一下可以做得到这件事情，可以做得到吗？这边有一个 sequence 挤进来，这边有一个 sequence 挤进来，然后这边的附近应该就要长成 wedge 的形式，这一边就一圈一圈一圈一圈这样进来吧，这边也是一圈一圈一圈一圈，这无限的一圈。然后
就做长成 H 的形，
我感觉这个 wedge 的形式需要一点 analysis 进来，或者 topology 进来，
呀，
不然的话解释不到。
嗯
所以这一圈哦，这一圈你如果放大一点，不是，其实它就是这一个跟这一个，然后这个边一个点嘛，然后这边附近的点应该要去这边，然后这边附近外面也有点嘛，应该也要进来这边，然后somehow 这边就是一个 wedge。
这个点一个点就可以去到两个地方。
没有没有没有不同的点，这个是一个点那边，一个点那边附近嘛，但是是在这个圈以外跟这个青色圈以外，make sense？这两个不同点，不一样的点，
或者它在那个圆上面，不是就在那个圆的保德鱼上面。
哪一个圆的吧？没有没有在原地方，所以是在这个圆跟这一个 deformation retract 的东西的中间。
不是中间。什么叫做 deformation retreat？
没有 deformation retract 的这个 space 的 complement，这两个的 complement，这两个的 complement，
这两个，一个保德鱼，一个
对，一个 boundary，一个这个 S1 的 complement，就这里面的东西啊。
嗯
呀，然后这里面的东西要来一要去到这个角落嘛，因为这个圈圈里面的东西我把它 information retrieve 去一个点，然后这个点就会 form 这个 x1，然后现在比较麻烦的是要解释 wedge point 这个附近发生什么事情，然后你要解释它的话，OK，不然的话可能如果用我这个解释的话，哎，我在讲不要几点啊，我们要开始了，
就是
所以如果你用无限的话。OK，先快点结束这样这个先。你看无限的话，它会这样子，这边会不知道发生什么事情，但是你也有这边在，
OK，
明白吗？
嗯，
所以你现在要解释的是为什么这些全部被挤去一个点。
就是这个圆圈缩成。
对对对对对对对对对
哦，
对对对。然后你要解释这个的时候，你肯定是要去解释这些圈跟这个以外的这些点怎么会挤成，就是 deformation retraction 这个地方。
OK，大概有
呀，
点，
有 idea 吗？
还有，
呀，因为你看啊这圈以外，反正是要这样子分散出去 retreat 的嘛，所以肯定是这一圈的东西可能要往这边挤了，然后这里附近的东西也是要往这边挤了，
很上，很上，然后就往里面挤。
对，往外面挤，往这个 wedge point 挤，
这样子这些是
哪一个？
这个是在那个圈里面的哈。
不是，你要这个是三维的东西的，这是三维的。说这一圈里面来，这个是z axis 嘛，你还有 x y axis 嘛，
OK，
然后就 radially
啊，
deformation 啊，那这个，等下再来啊，如果还卡的话。Okay, let's continue. Okay, so we will start the homology. So, in principle, homology should be easier than fundamental group because it is kind of a deformation retract. Okay, I thought it was deformation retract. It's a abelianization. Okay, so it's the abelian version of fundamental group. Okay, but there's a lot of tools we're gonna learn here. In particular, homological algebra. Okay, so there's a lot of tool to do calculation. Although the object is simpler, but the calculation will become harder. Okay, because this is the trade-off you have to make. Okay, this is the trade-off you have to make. So let's look at the motivation here. So fundamental group, right, cannot distinguish between higher dimensional sphere. Okay, for example, xn, because we proved that pi 1 of xn for x2 and above, we cannot distinguish. But then obviously we can define homotopy groups. Although we didn't touch this topic, we keep mentioning about this topic. This is the generalization of pi 1. So pi 1, you can think of it as you put unit interval into your space, but it's a loop. So the starting point and ending point is the same. But now pi n is to put a cube. Okay, put a cube, n-dimensional cube into your x. And then consider the homotopy as well. You see, homotopy is the same. It's just your space cross a unit interval. Okay. Previously was I cross I, right? Okay. So even if you go to higher homotopy groups, it's just IN cross I as well. But in general, it's very hard to compute. Okay. But then similarly for your pi 1, right? If your x is CW complex, your pi n is really depend on your n+1 skeleton only. Okay, like pi 1 only can view up to x2. Above than x2, then do nothing to pi 1 already. Okay, s2 already can make your either make your loop trivial or your loop is still non-trivial. Okay, because if you attach two cells, then your loops basically is
I'm trying to say that
True.
technically it's 0 or half of it.
Yeah. Okay, so then a more computable alternative is what we were gonna introduce, which is called homology group. So let us tell you what is the advantage first, and then we will see this advantage or prove this later. So first is the homology group Hn will be also only depending on n+1 skeleton. Okay, this is what we're gonna swear to you. Okay, we promise you. Okay. Second is nice thing about this homology group is Hi of xn will be isomorphic to pi 1 of xn. Okay, for all the I less than or equal to n. But it will vanish. Okay, it will vanish if this I greater than n. So very nice. Okay, it's kind of keep the fundamental group property here, or the homotopy group property. For higher Hi also vanish because if you have higher pi n also vanish. Okay. So it bears some similarity with fundamental group. Okay, so let's tell you what we're gonna do in this topic here. This is what gonna spend the next maybe 5 weeks. Okay, so we'll start with simplicial homology. Okay, it's kind of a restricted model using CW complex. And then we'll go to singular homology. So this is a more general theory. This is about the function into into our CW complex. Next, we'll just look at cellular homology. Okay, so this is more computable. Okay. So simplicial homology here, we are not just dealing with a CW complex. We're dealing for something more restricted actually. Okay, that's why it's restrictive. So what we were going to study is like bunch of triangle. Okay, bunch of triangle. Okay, triangulated surfaces or triangulated objects. We use triangle to build our space. Okay, we try to use triangle. Last time we used point, use line, use ball, right? Now we're gonna use triangle. So angle one. Okay, so triangle. And then lastly, we'll mention something about category theory. Estimatize this homology theory here. So we will see what's the algebraic structure or the structure that we have by defining this homology. So here we're kind of losing geometry. But the frontier of now, right, is to recover geometry through homology. So we kind of like replacing the geometry with algebra. Okay, this is what we're gonna do. Or if you heard something called the triangulated category, yeah, you can try and search it. So triangulated category is kind of category, some abstract category, some abstract theory, but we try to put metrics on it. This is done by one of my professor in ANU. So he made the address in the what do you call that meeting? The International Mathematics Congress. Or do you know that every 4 years they have a meeting? 4 years or 2 years they have a meeting. You don't know, you guys? You can search it up. Yeah, all the mathematicians can meet and then they share their important result. 没有result 去参加。Yeah, so that professor is very how to say, get a lot of grant. I think I heard them saying 2 million of euro. So he moved to euro already, from Australia to euro. He is about like already retired, but he moved to euro. He get a grant. So basically, what he do was he found a metric. So he put analysis back to algebra. But obviously, this analysis was based on algebra. So it's kind of bunch of commutative diagrams, category theory. So triangulate the category. So recover spaces, recover analysis from this category. Okay, so later you'll see a bunch of triangulated objects. You can put triangle, you use triangle to build it. Okay, let's look at some motivation. So let's look at the CW complex on the left here. Okay, so this is, if you see this very well before, right, because this is one of the covering space of X1, wedge X1. Okay, so let's just consider, let's consider all loops as the same circle. Okay, so whatever loop you see here is the same. For example, if you go A and then B inverse, or you go B inverse first and then A is the same. Okay, we don't care about base point here. No base point for the moment. If you are in the previous chapter, you want to fix the base point, but here doesn't matter. We just see circle as circle. Okay, it's like your assignment, X1. Okay, don't care where's the base point. So how to do this? This is possible by abelianizing operation. Okay, so meaning if I want to make this two circles the same, meaning I want to make the multiplication abelian. Correct or not? I can swap B inverse and A. So in this case here, we won't use this notation anymore. We just use additive notation because we know that 1 plus 2 equals to 2 plus 1. But our multiplication of number is still abelian, so that's not a very good analogy. But we will always view this. Matrix. Yeah, matrix good. Matrix addition is abelian, but multiplication is non-abelian. Okay. So by a byproduct of abelianizing is that we no longer have to pin all our loops down to a fixed base point. Okay, we don't need to care about base pointing. Okay, so in this case here, we no longer have to pin our loops to a fixed base point as we're choosing the loops. We're choosing the base point in the loop, just commute the letter cyclically. So first our loop will just become a cycles. This is what the term we're going to use in this chapter, cycles. Okay. So there's no base point, so we won't call it loops anymore. So usually loops will come with a base point, but if it's cycle, then we forget what's the base point. Okay. Okay, so in this case here, our cycles here, if we written as an additive notation, is just some linear combination of edges. For example, A minus B plus C minus D. So we just add these letters together. And we'll call this linear combination a chain. Okay, chain of edges. Okay, no, chains. You put a bunch of cycles together, become a chains. So this is some terms we're going to use more precisely later, but this is the idea behind these terms. Note that the cycles could mean any linear combination of edges as long as one of it composition into cycle makes sense. So meaning chains itself could be a cycle. Okay, chains itself could be a cycle. Okay, should we go through this? Let me see. Okay, maybe let's go through this. So what is the significance about this chain here? So in algebraic sense, we just require the sum of integer coefficient of each edges to be 0. This one makes sense or not? A geometry cycle will enter each vertex the same number of times that leaves the vertex. Okay, let me see this picture here. Okay, so if you look at this picture here, right? I think they purposely make this orientation like this. Okay, so it's like every path will come up from X and then go into Y. So in this case, if you want to make a loop, right? So meaning if you go up from X into Y, certainly you have to come up from Y first, and then going back to X, only you can form a cycle. So you can imagine that whenever you want to make a cycle, if you add up the coefficient, you will always be 0, because it will be +1 -1 +1. So this is the purpose of this CW complex here. Okay, so we can generalize this to old graph lah. So how do we generalize this? Well, we can form something called C1 and C0 here. So C1 and C0 here, what are they? Are you familiar with this kind of notation? Some familiar? Okay. So basically, it just says that every element inside the spaces, right, can be written as a sum of these element from sum of this space. I said uniquely. Okay, meaning you cannot find something times B inside something times B. Okay, they are uniquely. And then how do we group these? So I think you can kind of observe that A, B, C are edges. So it's like E1, one cell. And then S and Y are 0 cells, so they are 0 dimensional, 1 dimensional, like that. So we will frequently use this notation, Z generated by some elements here, to mean these direct sum. Okay, or sometimes we call this the free abelian group. Okay, so the abelian group here is just addition. And then, or more generally, this is actually called a Z module. Yeah, Z module. That's one. Yes. Yeah. So for this topic here, I think we will restrict our language to free a bit improve. But when we go to cohomology, maybe we will use module language. Okay. Right. So then we can define a very special morphism here. Okay. We can define a very special morphism here is I will send A, B, C, D to Y minus X. Can you make sense of this geometrically? Can you make sense of this geometrically? 把四个点变成 loop， 四个点是 loop. Not quite right because y and x is just a point. So these are edges. Okay, so what's the relation between x and y and these edges? They are starting point and end point, right? Okay, so they actually, where do they start at? Or they start with x and then end with y. So one is coming into it or one is coming up. Okay, so basically they make the coming up become minus, into it become plus. Make sense? Okay or not? Because there are two orientation on x, you can either come in or go up. So they make this into a plus and minus sign. Make sense? You can use different convention, but doesn't matter. So all of them will get sent to y minus x. Okay, because all the edges just connect to this two point here. Okay, later you'll see what's the significance of it. So if you look at this, first, what do we have here? If you have a boundary mat acting on this chain here, using this homomorphism, you can see that this is a difference between two linear combination of x and y. Okay. But then you can ask a question. Okay, what's the question you can ask here? So you can ask that when is this chain a cycle? So when is this chain a cycle? What do you think? So exactly when this k plus l plus m plus n is a kernel of this gamma. Okay, why? So maybe let's go back a bit. So for any arbitrary chain, right? What is the net number of time of this chain enter y? So it's just this number together. And then similarly, if you want to check how many times it leaves x, it's just the negative of it. True or not? Is it true? For example, you consider 3a. You do a 3 times. Right, how many times you move into y? And how many times you move out of x? One is 3, one is minus 3. So to make sure that this chain is a cycle, you need to make sure that this sum to be 0. Is that true? So meaning you cannot enter the y without leaving y. Correct? Does it make sense? You cannot enter y without leaving y to make a cycle. True or not? Like for example, is A a cycle or no? A is not a cycle because A enter y once. To become a cycle, you need to exit your y. So this exit can be obtained from other path. This exit can be obtained from other path. Okay, so this sum has to be 0. Okay, if this sum is 0, then that means this is the kernel of this map here. This is the kernel of the map. But what's the basis? Because this is a module, right? Or you should think of it as a vector space, actually. Okay. So you have a kernel, you have a vector space. One is 4-dimensional vector space. So you got a kernel. So you should ask what is the dimension? How to find dimension? Go to a first year, do row reduction. No? But what's the linear combination you want to, what's the matrix you are looking for? Can you see or not? What's the matrix you're looking for? So one is 4-dimensional, one is 2-dimensional. So what's the matrix you should form? Year one friendly. 4-dimensional to 2-dimensional. What's the matrix you have? You know how to write down the matrix? This is a linear transformation. Okay, maybe let's do exercise. How to write down this matrix here? Should be 4 by 2, right? Okay, then 4 by 2, right? 4-dimensional to 2-dimensional. Yeah. Domain 4-dimensional. Right. So here is 1 minus 1, right? Okay, because you map these to the standard basis, right or not? This is like, for example, 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, and then this one maybe 1 0 0 1 like that. Write down this linear transformation. So this is the linear transformation. Everyone sent to 1 minus. Oh yeah, 2 by 4 like this. Okay. So if you do row reduction, you will get this. Then what's the kernel of this? Okay, so the kernel of this, there are three free variable, right? Yeah, you can write down what is it. But the kernel is this A minus B, B minus C, and C minus D. Okay. Try and do this problem of the day, year one friendly. Okay. Yeah. Then second stage, compute the homology. This is not year one friendly. Okay. Yeah. Okay, this stage should be year one friendly.
放进去。
放进去啊，你会了啊，你会了，你再放进去不会也可以放进去的，但是要问对题目。Okay, everyone happy with this kind of basis? There are 3 of them. I think we choose this 3 Okay. Otherwise, it's just A B C D and like that. Right.
Oh yeah.
We choose this 3. Okay. And so thus every cycle in X1 is a unique linear combination of these most obvious cycle here. No, I mean from this calculation, right? The cycle should be A minus B, A minus C, and A minus D, right? Is it from this calculation? Yeah. So we do some base change. Okay, this is the technique we're gonna use frequently in this chapter. You can do base change. So please be sure you are doing the right base change. Okay, but so what's the geometric meaning here? So this means that actually these are the 3 basic cycles we have for this shape. Oh, is it true or not? Do you have 3 holes here? 1, 2, 3, exactly 3 holes here. So all your other cycles are built on these circles. Okay, and then one thing I want to remind you is this is also how we compute pi 1 actually. Okay, this is how we compute pi 1 actually. So if you look at the tutorial 4, right, there's something called the, maybe I want to point this out because I might give question on this thing. Okay, let me point out a bit. You go back and read. If you don't understand, we can do this class again. So check your tutorial 4. Yeah，现在动 tutorial 4。Yeah，我还没有拿出来，等一下我再开着。Tutorial 4. I add the extra question here. So this question is very important, actually. So if you have a connected graph, which we always have for our one-dimensional CW complex, then actually your pi 1x is actually is free with a basis of loops formed by the boundary of the bounded complement regions here. So this bounded complement regions is like what we see just now. So there are, if you look at the CW complex and then you look at the complement, so the bounded, how many bounded region you have actually is how many kind of loops you have. Okay, so for example, please read this. For example, in our case here, right? So you can see that the bounded complement region is like 1, 2, 3. Okay, so these loops were built for pi 1x. Also built our h1 just now. I haven't tell you what h1 but basically is to depict how many holes this space has. Okay, this space has like 3 holes. Okay, so this is computed by the kernel of this map here. Okay, the kernel of this map tell you there is a three holes, or we call it 3 cycles. So these cycles will bound the holes. Make sense? Okay 吗 ？Question 有问题吗 ？Okay, good. Okay, next，我们加一点难度啊，我们 put a 2 cell into it，放那个 2 cell 在这个第一个 hole 里面。What do you think? How many holes do you have now? How many holes do you have? If I add a 2 cell into it, 2 holes, okay. So you should expect the homomorphism just now will give you 2-dimensional, but this is not the case. It's not that direct. Okay, it's not that direct, but we still can have something that compute to these 2 holes. Okay, we shall see. The homomorphism you cannot change, right? Because it's 不管你有什么 hole 啊，我定义就是这个 S 进去出来肯定数量是一样的。But 怎么去看 how can we see this 2-dimensional thing? So we actually need a 2-dimensional vector space, a module or a free abelian group for this 2-dimensional thing. So just now we got C0, C1, right? 0 cell, 1 cell. Now we need to build another 2 cell, another vector space for 2 cell. Okay, or module. Are you guys okay? Module and vector space as changeable. They are the same because module is just vector space, which is not overview. Okay. Okay. Sorry? Yeah. So I mean, seriously, module is just a vector space, but it's not overview. Okay. So let's attach a 2 cell like that. Okay, we have orientation. So meaning we attach A and then B inverse. That's the orientation here. A first and then B inverse. Okay. Yeah. So what should we do here? Okay. So once we attach this, if you use the homotopy idea, right, you can see that what can you see? You can see that if you go A and then go back to B, this is the same as going from A to coming back to C. Why? Because your A can homotop to B. Correct. Okay. So in this case here, for example, A minus C and B minus C is equivalent. Okay, now. Okay, we want to make this to be true, but how to do this? Okay, we kind of want this to be true, but how to do this? So algebraically, we will do this. Okay, so algebraically, we will do this. So instead of C1 and C0, we will have an extra vectors module or free abelian group for this two cell here, which is just consists of generating one generator, which is A. Okay, so what this A do is I will go to A minus B. Okay, so what did you notice from the trend here? The trend here is we will tell you this homomorphism will tell you something about the boundary. How we glue this higher dimensional cell to a lower dimensional cell. Okay, I mean, what's their interaction of you? So then what we are interested is not kernel anymore, but the kernel modeled up by this image. The kernel still have three-dimensional things, right? But once we model up by this image, this will match our intuition for the two rows. Why? Because this image is A minus B. Still remember what's the kernel we had just now? A minus B, B minus C, and C minus D. But now you quotient out by A minus B. So you throw one generator away. Then this will make sense of the two whole, B minus C and C minus D. Okay or not? So what's the moral here? The moral here is you need a higher dimensional group to tell you what exactly happened. Okay, so in this case here, you can imagine that what we're going to do next is like we will keep increasing this chain, because once you know about a kernel of one, we call this a chain group. Okay, chain group. Okay, kernel of this chain group coming out. I mean the how to say that? Yeah, once we know the kernel of the homomorphism, then this might not be enough to tell us the geometric meaning of this map here. We need a higher dimensional map to help us get rid of something extra.
What is your
Yes.
1 and 2? H1, H2, what is 1 and 2?
X2 is the name of the new CW complex. And then H1 is this thing. So we define it to be like this. Definition.
So you mean this one means that it's
So this one could be following this boundary.
what do not mean when you see that sequence is standard and blue.
How do you
Because the partial one is right that
maybe you can order it like this.
is
The 0 degree, 1 degree.
so the H1 means it depends on what you do.
The kernel of the map coming out from the degree one. And then more out by the image of a map coming from n+1 degree. Does it make sense? Okay. Make sense? Okay. But similarly, what you could do is you can look at H2. Okay, if we generalize this one thing here, one n here. So this is like n+1. So if you look at H2, what happened? It is one dimensional. Is it one dimension? No, there's nothing, right? There's no kernel here, right? There's no kernel here. Yeah.
Your kernel?
H2 got kernel, me? Gamma 2. What's the kernel? This is a non-zero map one. There's no kernel map. I mean, like kernel is obviously zero, but so yeah, there's no non-trivial kernel. Okay, make sense?
We have also
Yeah, you can look at H0 as well. Okay, but H0 in this case is unless you want to extend this map to like C0 to 0, there's no negative cell, then everything is in the kernel. So basically, if you want to look at H0, it's just counting how many zero cell. Okay, so maybe let's compute something. Oh, I think time's up already. Maybe I quickly go through. So another thing is this is attaching two cell. Okay, can you see a two cell here? Okay, so if you consider two cell here, then your C2 is generated by two cell. Okay, and then both these two cells will do the same way, A and then B inverse, and then the other from the other side, A and B inverse. And then we can check that actually H2 has a kernel now, because you can take A minus B. A minus B. So exactly this is the S2 thingy. A minus B is the S2. So this is a two-dimensional hole. One-dimensional hole is S1, two-dimensional hole is S2. Okay, make sense? Okay, I think we can stop at motivation. On Wednesday, we can start a real thing. Yeah. Okay, so maybe you can cooperate with Eric to finish the typeset. Yeah. Then we will have yeah, so yes, cooperate with each other. Help yourself. Yeah, help your friend. If you want, if you already do exercise, you can help your friend. Then your friend can put you into the acknowledgement. All right. See you on Wednesday. Tomorrow. Yes. Yes. Yeah. Make sense? Yeah. Yep. Yeah. 就是用